Last time we studied logarithms, we studied the logarithmic function. Today we study their properties. Right, so exponential functions, right, have the laws of exponents. Right, study algebra. So you multiply same base, you have the powers, divide same base, subtract the powers, so on and so forth. Since the logarithmic function is the inverse of the exponential function, it only makes sense that they have similar properties. Let m and n be any positive real numbers, b greater than 0, not equal to 1. So all of these properties are going to hold regardless of the base. Just like the laws of exponents, it didn't matter what the base was. Log of a product is the sum of the logs. So log of m times n is just log of m plus log of n. This is known as your product law. Log of m over n, log of m minus log of n. So log of a quotient, difference of the logs, this is known as your quotient law. Log of n to the nth power, n times log of m. This is true for any real number n. As you take the log of a power, it becomes a scalar multiple. So this is your power law. These three collectively are the laws of logarithms, these three. There is one additional property that is useful called your change of base formula. Log base b of m. Log base n of m over log base n of b. So you can change your base using this formula. And if you don't have a calculator that lets you put in any base you want, this is the formula you'd have to type into your calculator. Generally speaking, the most common one we change to is e, right? So then it would just be ln m over ln b. But you could do it to any base. So you could also change it to base 10 if you wanted to. Or base 128 for some reason, whatever. Honestly, with the advancement of technology, this really isn't that useful anymore. Because just about now, all the modern calculators will give you the option to use whatever base you want. So this isn't even useful really that much. This is useful for understanding how logs work. So I could ask a conceptual question, right? Like, I give you values for log base 6 and then ask you for log base 11, and you have to use the change of base formula. So we'll tell you, these three are extremely useful in calculus. And also when we go to solve equations, we'll be using these logs.
So instead of typing in the first equation, we have to type the second one?
For the calculator?
Yeah.
Yeah, so let's say I asked you for log base 7 of 10. It would be ln 10 over ln 7 in your calculator, if you don't have the option to choose base 7. Right, and that's how you would then do log base 7 of 10. Yeah, so that's the workaround. And also, I think your calculator does have the option to do bases, but you have to search through lots of menus to do it. Probably be quicker just to use a change of base in that case. Now, all of these should be derived in the lecture video. Let's post it. Let's see where these come from.
So, if you gave us like, what's it called? There's no such thing as log one, right?
No, because we don't do base 1 because base 1 is a constant function, right? 1 to any power is 1, which is why we don't consider that to be a base. Right, so all of your base would have to be positive and not 1.
And there's negative bases, or no?
Okay, so in theoretical mathematics, yes. In terms of functions, no.
Okay, so
Because what we would do is we do -1 to an n, which is either going to be positive or negative depending on n, and then times b to the n. Is typically how we look at that. So again, in theoretical mathematics, yes, we do consider negative bases, but in this course we do not. That's some more advanced stuff. Right, so two other properties that are not listed here, so I'll just write them out. They're not really important enough to be considered a law, but so much. And these may have even been examined a little bit last time. So the first one log of 1 is always 0. And that you should have been able to find from when we looked at the graphs last time. Always crosses the x-intercept at 1. So log of 1 is 0. And the second one, again, is fairly obvious. This just comes directly from the definition of logarithm. Actually, I think it's supposed to be this. Log base b of b is 1.
So if it was like a log 10 of 10.
It's 1.
And is that
Because of what is the log, right? It's what power do you have to raise it to get what you're taking the log of.
Okay.
Right? So if it's log base 10 of 10, what power do you have to raise 10 to get 10?
Okay.
1, right? 10 to the first. Which is, I mean, kind of the same argument as being used for the first one as well, right? If you want to use an algebraic argument instead of a graphical argument, what power do you have to raise b to get 1? 0, right? Non-zero to a 0 is 1. But those are also two useful properties, right? The corollary of log base b of b being 1. So you can use that and the power law to do what I wrote before. Log base b of b to the n is just n. Right? Log and exponential functions undo each other because they're inverses. And so we'll now work with these. Again, what we're about to be doing, while not always necessary in calculus, it can make your life a lot easier. So this is known as expanding a logarithm. What we're doing is we're going to write it as a linear combination of simpler logs using
The quotient.
those laws. All of them, in general. Well, except for the change of base, right? That's for calculating. So yeah, the first thing that I would do is I'd notice, okay, I have a quotient. Right, I have a log of a quotient. Oh, and as is standard in any kind of algebraic problem like this, you always assume that all the values fall within the domain. Right, so they're all valid values so that the expression is defined. The log of the numerator, again, a note about notation. I would write that. That is standard to be that the xy is in the log, and not log of a of x, right? Log base a of x all times y. That is log base a of xy. If you want to avoid the ambiguity, you can put parentheses around it.
Just do it like log b and minus log bn, like that.
So that's what I'm going to be using. I'm just talking about the notation right now for if you're taking log of a product. We generally will not write parentheses around it. If we wanted log base a of x all times y, we'd write the y out front. So you might see that mixed notation. And then minus, because it's quotient,
Log a z.
log base a of z. Right?
And that's done.
Because look at that first logarithm. Isn't that a log of a product?
Yeah. So you have to do it again.
So the product law is the sum of the logs.
And then minus log a.
And that would be fully expanded. And so that would be its expanded form.
So would you say like this is as hard as this gets?
Yeah. Well, again, in terms of using the properties of logarithms, yes. Right, this is all we're going to be doing, right? It's just recognizing what laws we're going to be using to expand it out. And we will also be condensing, right? So doing the opposite. But it's all kind of the same. Now, the difficulty might be in determining when to use them. Right, and how far do you want to go? For our purposes, obviously we're practicing, so we're going all the way. Sometimes it may not be beneficial to do that, right? So that's where the difficulty would come in, and actually remembering them. So I have, for instance, I just did a Calc 3 yesterday, and we had to take a derivative of a complicated logarithm. About 95% of the class forgot about the laws of logs to simplify it. So also remembering them would be hard. And that's why I'm spending an entire class doing just the laws because of how important they are in Calc.
Yeah, but I think I gotta go to like Calc.
Because even in Calc 1, there was a technique called logarithmic differentiation. You need to know these. So it's kind of important. Log base a of x squared minus 1. This would be a case in, for instance, Calc, where expanding it probably isn't beneficial necessarily. It's fairly straightforward. But this can be expanded. And if you look at that surface, doesn't seem like there's anything you can do, right? It's log of a difference. There's no property for that.
Can you do the change of base?
Only if we're going to calculate what I do change of base. And that we're not. This just simply says expand. But x squared minus 1, that's a difference of squares, isn't it? So we're going to rewrite the log as log of x plus 1 times x minus 1. Well now that's log of a product, right? So you could write it that way. Log of x plus 1 plus log of x minus 1. That would be as expanded as it can get, right? And as you get really comfortable with these, you can generally look at it and immediately see how it's going to expand without going step by step, like we've been doing. I will just keep going step by step for today. So first thing, it's a quotient, right?
The bottom is going to be a product.
No, but we'll get there. I mean, technically it is, but we can do something else. So start with that. Okay, we have a fraction, so let's write it as the quotient law. Difference of the logs. Now if you look at that first log, and so again, just keep going piece by piece until it's fully expanded. And that first log, it's log of a product, right?
So you started out doing the quotient.
Mm-hmm. So first log we can write as a sum. Now look at that second piece, the minus. Yes, it is technically log of a product, but there's actually something else it is. It's log of a power, isn't it?
That's true.
So you can use the power law.
But could you use the power law?
You could, and it's going to give you the same thing, just with a little bit more algebra. Power law says you bring the power out as a scalar. And if you did it as a product, you have minus the quantity of log of x minus 4 plus log of x minus 4, right? Which is 2 times that. So you see, you're still going to get the exact same thing. Right? Look at each piece. Is that fully expanded? So can we expand out this first log?
Yeah.
Yeah. What is it?
It'd be like log a, it's a product.
Again, technically, yes.
Powerless.
It's a power, though.
So
So use that power law, right?
3, it would be log a 3, or 3 log a x.
Can the second piece be expanded?
No.
What about that third piece? And then you play the same game. You just go piece by piece. Now, well, we already know those last 2 pieces can't be expanded any further. So just look at the first piece. Can that be expanded any further, or is that as far as it goes? So you don't. That's the fully expanded version. Just done with that problem. I just throw it on the ground. Just done with it. So two problems, both involve 2 problems that involve quotients. You should have noticed the pattern. What law was used first? quotient law was done first. And so again, this is typically how I approach the problems. First, look to see if it's a quotient, use that first. Then product. Then power. In that order.
Quotient. But
You
since
could do that.
But since it's under, you can do a power.
In this case, I would actually do the power first. Because you're taking an entire quotient to a power, right? You don't have to, right? So again, there are two ways to approach this. And they both kind of lead to the same thing. I did both ways, and really one's not shorter than the other. Right, so the first you could do is recognize, oh wait, if you take the square root of a quotient, you just distribute the square root through, right? So it'd be square root of the numerator over square root of the denominator, and then proceed from there.
So would that be like, would that make it like x to the fourth?
Mm-hmm. So square root doesn't distribute.
Just take it away, right?
Yeah, square root doesn't distribute. No, square root doesn't distribute across addition. So it would just be the square root of x squared plus y squared. You can't simplify that. If that was x squared times y squared, then yes, you could. And then square root of x times y. You could technically write that as square root of x times square root of y. Whatever. So that's the one thing you can do. Make it simpler in terms of how many times you're writing the fraction, is just to recognize that's a giant power. Do that first.
Yeah.
Right, so that's what we call the exception to the rule of doing quotients first. What power is square root?
2. Square root.
Yeah. That's the index of the square root. I'm asking for the power of the square root. Right, so if you were asked to write square root of x in terms of a power of x, what would the power be?
Negative.
That would be 1 over x squared. Right, remember, negative just means reciprocal.
I've never heard that question before. One. 0. Power of 1/2. Wow.
Fractional exponents.
But I thought, like,
So the appropriate law
yeah,
that looks familiar now.
yeah, but
So whenever you have a fractional power, the numerator is what the whole thing's being raised to, and the denominator is the index of the radical. Right? Because there's actually two ways to write that. You could write that or this. And they mean the same thing. Since the power is 1/2, right? 1/2 times the log. And remember, the game you always ask yourself, can it be simplified further? It can. What would we use?
quotient.
And remember, the 1/2 applies to everything. go piece by piece. That first log, can that be expanded any further?
Like you took the 1/2, or
Just the log, ignore the 1/2. Remember, we're just looking at logarithms.
yeah,
So just this right here. Can that be expanded any
yeah,
further?
with the powers.
Get it? But so you're right, there are powers in there, but is it an entire function to a power?
No. Yeah.
And there's no law for log of sum, right? That is as expanded as that's going to get. There's nothing you can do with that.
But the other one you can't.
Not in the real plane. If this was the complex plane, then yeah, that's technically a difference of squares. Do a product and all that. That second one though,
You can
that is, what law is that?
product.
And then again, be careful, because it's minus however you simplify the log. So again, you're going to need parentheses. And the product says it's the what of the logs? Right, so log of product is
What?
sum of the logs. Before we do any simplifying, are all of the logs fully expanded?
Yeah.
Now it's just a matter of distributing.
Oh, you gotta distribute it.
Yes. And that's how it would be written. Because generally speaking, the idea is when you expand, you want to write it as a linear combination of logarithms. This is the proper form of a linear combination. Constant times something plus constant times something plus constant times something. Well, technically, yes, this is a linear combination, it just doesn't look like it. It's not the correct form. Right, so this is how we write it. As I mentioned, once you get to other classes, it's really a matter of how far is enough for you in terms of the application. So what'd you do first?
Product of it would be ln plus
ln of what?
my, I thought it would be like ln minus. Isn't that the product thing? It's a minus.
Product is not minus, quotient is minus.
Plus thing.
But remember, ln is an operator. ln by itself doesn't make any sense. It has to operate on something.
And then e. Or no, that's the same thing.
So look, you said it's product, which I agree. What is the product of? What times what?
Oh, the CE
So what's your first term of the product?
1. First term.
So ln of c e to the 5x plus 1, I agree.
Yeah.
And I do agree that's a product.
Yeah.
What are the two terms? Right, so,
And
all right, that's a product, right? What's the first term of that product?
2 there.
What's the second term?
2.
So now apply that logic to this problem.
ln times c e to
Just ln of c. That's c
Oh.
times e to the 5x plus 1, right?
yeah.
So your first term would be c, so it'd be natural log of c. Right?
Yeah. Plus e. Okay.
Right? Plus the natural log of your second term, which is e to the 5x plus 1.
Because like the ln is kind of like getting distributed,
Well, again,
or not?
that's not the right way to look at it. Natural log is an operator. So it has to operate on something. You can't just say log. That doesn't make sense.
Yeah.
So it's log of something. Right, so that's why you can't say that's ln times c. That's not what that is. That's log of c.
Yeah. Okay.
Right? Does that make sense?
Yeah.
Like, again, context matters in that. This was something I saw a lot. In terms of functions, that's not f times x. That's f of x. F is acting as an operator. It's operating on something. But there are cases where maybe that is f times x. Right? F might be something. So context matters a lot. But it's the same idea, right? Natural log is a function, right? It has to operate on something. Can we keep going?
Yeah.
How?
With the sum product, or I mean the power element.
Okay, I agree. So what would you write?
I would write the 5x plus, oh wait, no, ln c. And then I would write, e. I would write plus e.
That.
Plus e.
What you're saying first, we're starting off correct.
Yeah.
So how do you say 5x plus 1?
Yeah, because I know you put the power in front.
Yeah.
Right?
Yeah, 5x plus 1 is your power.
Yeah. No, that's what I was going to do with the
Yeah, see? 9 times out of 10, don't question yourself, your first instinct's right. Can that go any further?
yeah,
How?
the product.
We have a natural log of products.
Could that be the LNC or no?
And so again, it's not a product, that's natural log of C, right? You are right though, that can go further.
Because 5x plus 1 is getting plus or times by the LNE.
Specifically one of the two that are written above. What's the base of ln?
E.
And what are you taking the log of? natural log is log base e. So natural log of e is just 1. And that would be as far as we needed to go. I'll just reintroduce that common convention in math. If we continue to assume that that capital C is just a real number, which generally in math, a capital C is a scalar, then we could actually simplify this even further.
It would be log e of the number.
Right? Log of a constant is a number, right?
Mm-hmm.
So why not just write it as a constant? Right? A new constant, call it, in this case I called it C1.
So if it was like, what's it called? So basically, if it was like ln5 or something,
That's a number.
You could just put that into the calculator and then get the number.
Now, I would typically just leave it as ln5, because that's not a nice number. That's an irrational number, so just leave it as ln5. But in math, if it's an unknown constant, you typically want to write it as simple as possible. Right? So it'd be convention to write, for instance, natural log of c as just some number c1. Just looks nice. It looks cleaner in your solutions. And actually, I could go even further. So I wouldn't even stop here. This isn't as clean as it can be. C1's a number. What's a number plus 1?
C2.
It's a number. That's typically how we represent it in math. That's the cleanest it can be. Right? You just collect all of your constants together into one constant. Now we're doing the opposite. This is known as condensing. Right, so we want to write it as a single logarithm.
So first notice that there's a power one.
Good.
And then I noticed there's a minus, so that's like a
So what law is that?
like a quotient.
There's your single logarithm. And so go term by term.
There's a power, so it'd be like log a 5 to 1/3.
Yes. Now in mathematics, conventionally, if it's a constant raised to a fractional power, we'll write it as an index, as an indexed radical. Even though you're not incorrect to write 5 to the 1/3. It's just more conventional, right, as cube root 5.
And it looks better.
right? If it was x, again, convention would say that would just be x to the 1/3. Kind of an unwritten rule. Second term,
That's another power, so it'd be log A, x to the 3rd, but
so what would the sign then be between them?
up plus, or minus, since it's in -3.
You could have also written that as plus and then used -3 as your power, right?
That's true too.
So both ways are valid.
Then there's another power, so you could do that, or, yeah, minus, and then log y to the 4th.
And so from here, a couple ways to proceed, depending on what you want to do.
There's the minus, so that's a quotient.
Which minus? Because there's two
Um,
minuses.
I prefer to do the log A x to the 3rd minus log A y to the 4th, because there's no radical.
So there is a problem with that. There's also a negative attached to that first log. So you wouldn't be able to simply do that as a quotient, because both of them happen to have a minus sign in front.
Alright, that's fine. Then
I know what you're getting at. And what you would do, because that's the way that I'm going to proceed, is to first factor the minus out. And then notice that that log is a product. And then you see the quotient, right?
And it matters which one goes on top. The first one would just go on top.
Well, yeah, in this case, yeah. As long as it's not a minus in front, right?
So if there was a minus in front of that one, you'd have to
Factor the negative out of all of it.
out of it again, and then so the whole thing would just be a
Yeah, it would all be in
minus.
the denominator. The other way to proceed is to just read it left to right.
And that's another quotient.
Right, which would be this mathematically.
Yeah.
But then what's the rule when you divide? Right, it's the numerator times reciprocal of the denominator. So it'd be that times, what's the reciprocal of y to the 4th? 1 over y to the 4th, right? And how do you multiply fractions? Multiply fractions straight across, right? Right, so this would be times 1 over y to the 4th, and you just multiply straight across, which would give you the exact same thing. Right, so it doesn't matter which way you want to proceed. I typically like to just group all of my positives together, all of my negatives together, do all those together, right? You get a product minus log of a product, which is going to be one nice looking fraction right off the bat. Without having to deal with, oh look, I'm taking a fraction over a fraction. right? But you'll get the exact same answer. Right, so that's typically how I approach condensing. I do get rid of all the coefficients first, using power law, and then I'll group all of my positives together and all of my negatives together. I obviously factor out the negative like we did in that second step right there. Factor the negative out of all the negatives. Right, so recognize you have coefficients. Deal with that first. So 1/3. So be careful how you say it. If you said to the third power, which would be cubed, what do you meant? 1/3.
Then minus.
And again, convention is to leave that as a fractional exponent instead of a cube root.
Log a x the negative. Yeah.
You could do -3.
What?
Because I could then just write this, right? Plus -3. Right? Because you can read this here as that, right? And when you have a negative exponent, what does it do? Reciprocal. So it'd be the same thing as saying you're still dividing by x cubed. So it doesn't matter how you do it. You can either take that as a negative exponent or positive exponent and leave the minus sign.
Would that make it harder if you had a negative exponent to like do the quotient and stuff like that? Cause
Well, if you're going to treat them all as negative exponents, you wouldn't ever have a quotient, would you? Because it'd always be log plus log plus log plus log.
yeah.
And then you just use the exponent law to flip all your negative exponents into the denominator. Maybe what plus log of
1 to the second power. And then you have a quotient
you can.
or the product.
So again, how you proceed from here doesn't matter. You could just go left to right, right? You're gonna have a quotient, and then another plus, which is gonna be product, which fraction times something simple. The way I typically proceed is I just, as I said, group all of my positives together, all of my negatives together. So I would just do my two positives first. And I'm going to avoid the ambiguity and actually do put brackets around that. And then just the 1 minus. Now it's a quotient, right? Over x cubed. That would be fully simplified. Or fully condensed, rather. Which, oddly enough, I think is simplified. I think that's what they call that, simplification. Right, going with what you were saying first, you have this, right?
And then,
Which right away, the very next step would lead you right to that. Because again, how do you multiply fractions? You just multiply straight across. Numerators, product of numerators over product of denominators. So that didn't even add any additional confusion. So there's two ways to approach this one.
put the whole thing under a radical.
Well, that would be the very last step,
Oh, yeah.
if you do that way, which is,
Yeah,
that is the approach, by the way, that I'm going to take.
do that way. That's
Right.
much easier.
The other approach is just distribute that 1/2 through first.
That's like,
And then do it.
that makes it so much.
Again, it doesn't matter because you're going to wind up with the same expression regardless. But yes, I am going to just do the parentheses first. So leave that 1/2 alone and work with what's inside the brackets. That first term, nothing to condense, right? There's no scalar. That's just log A of x.
Oh, yeah, good.
And then log base A of y cubed. Like that, right? That was a product, right? It would be that. Log base A of xy cubed. And then just minus that other log, right?
And then all under a radical?
But I'm not done yet.
Oh, the minus, the quotient.
When you do the quotient, right? And then, yes. So again, two ways. You could either put parentheses around it, raise it all to the 1/2 power, or a square root. Either way, it doesn't matter.
But like, how would you even like, do the other way? Because would you like multiply, 1/2 times 3? And then it would be like,
Yeah, which would be, so you have
so 1/2 log.
1/2
Log x.
plus 3/2 minus 5/2. So each of these exponents, get rid of the square root. Right, get rid of the square root. Each of these exponents would just be over 2. So that'd be x to the 1/2, y to the 3/2, z minus 2 to the 5/2, which is the exact same thing as this. Right, because if you just use the 1/2, right, you put parentheses and it'd be all to the 1/2 power, and then doesn't that 1/2 distribute into then everything? So, as I said, no matter which way you approach it, it's going to be the exact same expression. It's just a matter of which way do you want to go.
Like something on the radical at the end.
And also remember that math is a lot of aesthetics. Right, how you write the expression, because there are 3 ways I could write that? 4 ways I could write that, actually.
The final one?
Well, more than 4. Oh my, there's a lot of ways I could do that. It's just which one looks the best in your eyes. Right, I would pick one of these two. personally. To me, that just looks, one of those two looks the best. But you could do this. Right.
Those are all the same.
You could just, I don't have enough room to write all of them out, put this in parentheses to the 1/2, and then 5/2. Or square root of the numerator over square root of the denominator. Or square root of x times square root of y cubed over square root of z minus 2 to the 5th. They don't look as nice, in my opinion. Too many square roots.
Yeah.
Right. Same thing with this, in my opinion. Too many halves. Reduce as much as I can. But again, it's entirely up to you. So we're going to write this into a single logarithm. Hold on.
Is it wrong?
I got natural log happy. It's supposed to be that. So let's fix that. So we have obvious steps, right?
Power.
So let's do all those obvious steps first.
So it would be like ln x plus 1 to the half power, and then minus ln x minus 1 to the half power. Plus 2.
And then you have another obvious step.
And then the quotient. Plus 2.
Which I'm going to rewrite.
And then we get to the product when we're done. Yeah, that makes more sense to me.
I'm going to use just the square root because I like the way it looks better, but you could just raise it all to 1/2 power, that's fine.
And then you could do the product rule.
Can you?
So it's plus. Oh wait, no, there's no what's it called?
You're not wrong, though.
Hmm.
This is a product.
Oh. How would you get, like, look at me like that then? I didn't think I was wrong.
Because I knew where you were going. You have to change C first before it becomes a product, right? Because the product only works if it's log plus log. So how can we write C as a natural log?
Log C.
That's something different. So take 5 versus natural log of 5, are they the same? No. This is where manipulation is really handy.
Oh, there's like a 1 exponent.
So do that. Plus natural log of e to the c. Right, remember the logs and exponentials are inverses of each other, right? So if I want to do natural log, I also have to take it as a power base e. Now I haven't changed anything, right? That's still the exact same value. Now it's product. Now it's a single log, right? But you know what? I still don't like that.
I'm going to take out the square root and add it.
I'm gonna write the whole thing under a square root.
E to the c times the fraction.
But I can't. It can't be e to the c. Because again, same argument. 5 versus root 5, are they the same?
So it would just be c.
What is the opposite of the square root?
Power to.
So make that e to the 2c under the square root, and it's the exact same thing, right? Because that'd be e to the c squared.
But you wouldn't be wrong if you
No.
just kept. That's the difference.
Again, how would I write my answer? That last one. How would it be written in physics? Probably that last one is how it would be represented in physics. Let's get it all under the square root. Oh, yeah, you can see this. Take this.
You're done.
Going to start working some change of bases, but before I do that, are there any questions on the expansion and convention? Again, wanted to focus on that because that will be a very useful skill in calculus. So write down your laws of log somewhere, and make sure it's somewhere that when you move on to calculus, it's in the exact same place so you don't forget them. So I promise you're going to.
Let me go back.
Can I? I can.
So when we do this,
Will I go back to them, right? That's the real question. And don't forget, these slides do get posted. So it's not like you ever lose them.
so if when we do change of bases, all we do is just put that thing into the calculator and that's it.
When evaluating, yes. So we'll get to it. Once I make sure that we're no more questions on this. Excellent. Then let's look at the change base. So the idea is we want to write this logarithm as base 10. We're not going to evaluate it. I'm just going to actually write out the change of base formula.
So
Actually, maybe I will. Maybe I will also evaluate.
we would just put log 10 parentheses 55.875 in the calculator.
Not just that. Right, because if you change the base, you actually are changing the answer. So remember what the change of base formula was.
It was like the M.
Since we want base 10, I'm not going to worry about writing log base 10, right? Common log.
55.
So it's log of what you're taking the log of,
Over.
divided by log of the old base. And this is actually perfect because my calculator can do base 14, so I can actually show you both evaluations. And keep in mind, that was base 10, right? I could have used any base, and I'll show that off as well. This was the original, so let's do log base 14, 55. Why am I using the mouse when I opened up my keyboard? All right, so there it is if you just type in log base 14, if your calculator allows you to do that.
So that would just be the answer.
Now let's do the change of base. Yeah, so that would be the answer. If you can do it, and I say evaluate this.
Yeah, so if you gave us that question on like a test or something.
So it depends. If it's the question exactly as it's worded, oh wait, I have to go back. Then I'm asking you to convert it to base 10. So what I have written would be your answer.
Okay, so it wouldn't just be the straight up answer.
If I'm saying evaluate this,
Then you just put it into your calculator.
right? Yes, then it could be that. And I tell you how many decimal places I want. It'd be that.
Mhm.
Or you can use change of base if you don't feel like digging through how to find base 14. So they wanted base 10, so let me do base 10. Right? Common log, I'm not going to write the base. 55.875 divided by common log of 14. Oh, it's the exact same thing. Oh, but again, if I'm just asking you to evaluate it, you don't have to use base 10. The most common one to use is base 8. So natural log, 55.875 divided by natural log of 14. Uh-oh. What happened? That's not good. Oh, okay, I see what I did. I accidentally did 55.874 instead of 0.875. Whoops. Let's fix that. There we go. I don't think there's a way I can just get rid of this, can I? I can, yes. Oh, look at that. It's the exact same thing, isn't it? Right, so again, if I'm asking you to evaluate it, if you don't feel like digging through your bases, use change of base formula. Easiest one to find would be natural log. So that's how you type it in this last one. And it would give you the exact same thing as if you wanted to dig through and find base 14. So let's go back to here. I honestly don't remember what text I got this out of. I don't know if it's your book or if I used a different book. But so this is kind of what I was saying at the start of class as a kind of conceptual question. on using change of base. So they're telling us that log base 5 of 6 is equal to A, and log base 5 of 11 is equal to B. We want to evaluate these three values. So start with log base 11 of 5. And we're going to use all the properties of logs.
So we don't just put that into a calculator?
No, because they told us A and B, so we want to write it in terms of A and B. Well, they gave us what? Base 5, right?
Yeah.
So we want to convert to base 5.
Oh, so we would do a log 11, or just 11?
Log base 5 of 11.
So they gave us, so we would have to do A as well.
Well, if there's an A, there isn't in this case. What's log base 5 of 5?
1.
It's 1, same base. What's log base 5 of 11?
You need to calculate the,
Look what they told you.
oh, B.
There's your answer, 1 over B. Right, so again, yes, I mean, this is going to have some numerical value. I don't care what that numerical value is. We want to use in terms of A's and B's. And possibly whole numbers, right? No decimals. Next up was log base 6 of 55. Write it in terms of log base 5, right? Because that's what they gave us.
So we're just going down the list.
These problems, yeah. So this is number 28 that I'm working on right now. Did they give us log base 5 of 55?
No.
Oh, but isn't 55 5 times 11? And then that would be a product, right? So we can write log base 5 of 55 that way, right? Log of 5 plus log of 11, because 55 is 5 times 11. What was log base 5 of 6? So that's over A. What is log base 5 of 5?
1.
Log base 5 of 11. There's your result. Log base 11 of 6/11ths.
If you log 6 and 11.
Again, start with, you want base 5, right? Because that's what they gave us. So change your base formula. Log of 6/11ths over log of 11. But they didn't tell us log of 6/11ths, right? But that's a quotient. So we'd be able to write this, right? Log of 6 minus log of 11. over, what was log 5 of 11? What is log base 5 of 6? Oh, log base 5 of 11 we just said was?
ED.
Here's your result. A minus B over B. Right? So again, this is more of a conceptual kind of task. Understanding your properties. Again, I do not remember the source. I don't remember if this was your textbook or a different. So put your calculator away, because they want to see you evaluate all of these without the use of a calculator. Oh, that first one's kind of simple. This doesn't require any kind of work. What is log base 3 of 1/9? Is 1/9 a power of 3?
Yeah.
What's the power?
3. Or 2.
3 squared is 9. So I agree with that.
Yeah, 3 squared.
But that's 9, not 1/9.
1/3. So 3. 30.
So 3 to what power is a 9th?
2. So 1/2.
I agree, 3 squared is 9. How would you make 9 1/9?
-2.
-2. Right? Oh, what's log base 3 of 3?
1.
That's just 1. That is -2 minus 3, which is -5. And that one required like no work whatsoever. Now comes the fun one. Six log base 8 of 2 plus log base 8 of 64 over 3 log base 8 of 4.
So it would be 1/4.
So first ask yourself, is 2 a power of 8?
Yeah.
It actually is, yes.
1/4. 1/4.
So you're doing 8 times the fourth, which is not what we're looking for. It's what, so it's 8 to what power is 2?
3. 1/3.
1/3 power, the cube root of 8, right?
Damn, I would have just gotten this question wrong before.
So you could have done that. I'm not going to go that route, because let's just say you don't see it right off the bat. Do this. Just write that as log base 8 of 2 to the 6th. I'm not going to evaluate log base 8 of 64 for a reason. What is 4 cubed?
4 cubed. 64.
Look at that. That's just 1, isn't it? Right, so this term here is just 1. Now, here's how you can easily see
12.
what we're going to get.
You do 2 to the 6th, don't you?
I'm not actually going to evaluate what 2 to the 6th is. Here's how I'm going to do it. 2 to the 6th.
That's like,
Isn't that 2 cubed all squared?
yeah,
What's 2 cubed?
2 to 8. 8,
And it's base 8.
1.
So 2 to the 6th is the same as what? 8 squared, right?
Yeah, so it's 1.
So
It's just 1.
this
I was there for 1.
is that, right?
Yes.
And it's base 8. So what's the power of 8 here? 2. So what's log base 8 of 2 to the 6th?
2.
2.
2 plus 1.
Like going this way, the way that we were going at first. Log base 8 of 2 is a third. What's 6 times a third?
3.
6 times a third.
6 times 1/3.
And so 6 divided by 3.
2.
2. 2. See that? So multiple ways to approach this, right? Come on. Okay.
So you wouldn't do one of these on a test, right?
Might.
That's crazy work.
I'm not going to deal with trying to figure out power of 9 that gives you 3, even though it's fairly obvious.
Wait, so could you realistically do log base 9, 3 to the 2nd power?
That's what I just wrote out, right? Log base 9 of 3 squared. What's 3 squared? Log base 9 of 9. So that's exactly what I'm doing. That's 1. That's what I'm doing, right?
So realistically, if there's a number before the log, you could just put that as a square?
As an exponent, yeah, that's what I'm doing. Again, because I'm using all the laws of logarithms. What's 3 to the 4th? It's 81. Or 3 squared, 9 squared. I'm going to write it that way,
That
just
equals
to
2.
really make it obvious. Oh, okay, well this one's going to be fun. 729. Is that a power of 9?
Yes, it is.
What power?
It's the power of 9.
9 to the 9th is way larger.
4.
Close though.
2.
3.
Yes.
Right. 9 squared is 81. 81 times 9 is 729. But that's 1 over 729, right?
So it'll be 1 over.
So it'd be 9 to what power? Minus 3, right? Because I want to take the reciprocal first to get it as 729, and then go 729 is 9 cubed. Oh, well, now you should easily be able to see what we get. It's 1 minus 2 minus 3, right? Which is -4.
Can you go over how you did the 1 over 729 again?
So the first thing I did was look at 729. And I said, okay, well, is that a power of 9? And it is. I recognize it as 9 cubed. You can easily find that by going, okay, well, I know 9 squared is 81. 81 times 9
So
is 729, right? Nine times 8, 72. So 9 times 80 is 720. And then plus 1 times 9. Oops. So if 81 times 9 is 729, that means that 729 is 9 times 9 times 9, 9 cubed. So that's how I recognize that as a power of 9. Right, so now we know that 729 is 9 cubed. But that 729 is in the denominator, isn't it? How do I make the denominator numerator?
negative.
Negative exponent. So that's how I know it's 9 to the minus 3. Does that make sense?
Yeah.
That's typically how I look at fractions when I deal with powers. If it's 1 over, I just look at the denominator and then make it a negative exponent. Any questions? We're almost done, by the way, with exponential and logarithmic. Which is the easiest thing we do all semester. So the homework on laws of logs, again, not due next week because next week is spring break. Will be due the following Wednesday, so March 26th, which is the same time as your project being due. Don't forget, next week is spring break, so we're not meeting at all next week. Oh, I should put this on here. Meant to do it. Next Tuesday is the 18th. There will be a short spring break assignment that will post on Blackboard on the 18th and be due on the 24th. It's a real simple assignment. It's going to ask you to pick 3 problems from the course, plug them into a generative AI, and evaluate what the AI gives you. Right, so you have to obviously enter the prompt. You want to copy and paste the prompt and its response into the report, and then kind of just analyze it. Did it do it correctly? Did it make a mistake? If so, what was the mistake it made? There is also a bonus opportunity on there as well for extra credit.
Maybe tell us what that is now.
It's on there. I don't remember exactly what it is. I think it's something along the lines of find a problem where the AI makes one of these 3 mistakes. Right? So find a problem where it makes this mistake. I don't remember what the exact mistake is. Find a problem where it's going to make this mistake. Find a problem where it makes this mistake. That's your bonus opportunity. That's the extra credit. But again, it's still using generative AI.
I'm gonna just plug one of your long equations into there.
That's fine. Pick one of the examples that we did. That's the whole point of the assignment. That's just pick a pop from the class. Have a great spring break.